There we go. All right, so last time we got into 1.5. I tried to use Smart Notebook with my tablets here, and my handwriting was horrible. So we swapped it out. I lost a bit of time. And so I kind of swapped it out and brought back the OneNote. I don't love the OneNote because when I print or when I submit, make the notes into PDFs, that's when you'll see these weird, like the page will just cut off in the middle of something. So it's not perfect, but it'll work for us. And so I'm gonna make it a point to always use this because it's the only way my handwriting is readable. And so the last thing we did, we grabbed the question off of the last page of the PDFs, got 2 points, created a linear model, defined the slope, defined the intercept, and then discussed what does it mean, what is the Y value, what is the estimated systolic blood pressure for someone 55 years old. I mentioned quickly in passing this page, which is page 3 of the old one of the notes that you have, which has on-base percentages and runs scored for teams in baseball. This is obviously not this year's data. This is from the textbook. And they've got them paired up on-base percentage and runs scored. So what I'm asking you to do in this is look at the scatter plot on Desmos. So what you're going to do in Desmos is this. You're going to take, I'm going to hide this line really quick so you don't see it. So if you plot all of those points, you're going to go up here to the plus sign. You're going to hit table. Table's going to pop out X1, Y1. All the X1s here, all the Y1s here. Make sure you pair them up, as you know. And then the problem is if you type them all in, but you do something silly like me and use the standard window, you're going to find out that none of this shows up. There's nothing on this graph. Okay, I graphed all those points, I've put all those points on there, and now there is nothing there. The reason there's nothing there is because my window doesn't show them. My window needs to accept the lowest X value and the highest X value. My window needs to accept the lowest Y value and the highest Y value. Now, I don't think there's a fancy way to arrange these. So we're just going to run through, find the smallest number. I think it's 31.9. And then find the largest number, 30, see a 35, a 34 in there, 34. Yeah, 30, so 31 to 34. And then for the Y values, the lowest, there's a 600 something here. And then there's an 834 here. So 691 to 834. So in Desmos, I use the little bar up here. On a calculator, you would use the X-min, X-max stuff. Lowest Y value I need to represent is 30. The highest was 34, so I can do 30 to 35. If I stop there, I still don't have any dots, still don't have no scatter plot because I haven't moved the Y yet. So the Y values, the lowest was 691, so I'll go down to 650, and then the highest, 849 is the highest. So if I change the window to no, you will not need a graphing calculator on the test. Y-axis 650 to 850. And there are all of our points. You can, on Desmos, you can grab and drag, but here's our scatter plots, okay? So we're asked to take a look at this scatter plot. Yes, Desmos is going to have to be available. So, but we'll work on that. We're going to figure all that out when the test comes around. So yeah, if either you're going to have access to Desmos or I'm not going to give you test questions where you have to do all this. Okay. And probably I'm not going to give you test questions that require the use of this. But yeah, if I do give you a test question and it is required, then yeah, you'll have access to it. All right. So does it look like, do you see any pattern here? Okay. Do the data appear to be rising from left to right, falling from left to right, staying steady from left to right, or maybe they don't have any relationship left to right? It's not super strong, but we can see that my data seems to, as X increases, Y increases. And remember, what are these values? X1 is the on base percentage, Y is the runs scored. So it would seem that our graph is saying the more often we're on base, the higher our on base percentage is, the higher the total runs scored for the team. That makes sense, right? So there's the plot. Second part of the question. Whew, I want that to get out. Second part of the question, write our own linear model. So to do our own linear model, we're going to pick 2 points, find the slope, and then write the linear equation based on that. So I can pick any 2 points I want, and but except for the first two, because they both have the same x value. So if I pick those 2 points, x values are identical, that means I'm going to have a vertical line. So I need to pick something that has different x values. Desmos does give it to you, but that's the linear model from Desmos. Okay, so we're going to make our own, and then we're going to look at the linear model that takes into account all of the data. All right, so let's look at Florida and Milwaukee. All right, so the 2 points, and this is how the problem has been done. This is how we've done every one of the problems so far. We create our own linear model by taking 2 points, 32.7, 730. We find the slope of the line, change in y over change in x. 730 minus 758 over 32.7 minus 33.1. 730 minus 758 is negative 28. 32.7 minus 33.1 is negative 0.4. And 28 divided by 4/10 is 70. Okay, and negative divided by negative is a positive. So there's the slope. What does this mean? Okay, a slope of 70. Okay, what's my y values? These are runs, right? What is my denominator? Well, this 70 is written as, it's an integer, so I can rewrite it as itself over 1. What was the units for the denominator? That's the on base percentage, the OBP. So it looks like for every increase of 1 point in the on base percentage, a team has an increase of 70 runs scored in the season. Okay, that seems like a lot, but remember, on base percentage, look at it, it's everything in here is between 31 and 34, or 31 and 35. So just going from 30 on base percentage of 30 to 31 or 31 to 32, that's going to increase your number of runs by 70. That's amazing. All right, so if that is my slope and I have these 2 points, I need to write the linear equation that represents this line. That is y equals mx plus b. To write the equation, I need the slope and I need the y-intercept. I was not given the y-intercept, so I'm going to have to go find that. I'm going to find b, and I'm going to use just the first point that I run into, 33.1758, and a slope of 70. So y is equal to, whoops, y is gone because y is 758. Slope is 70. X is 33.1 plus b. 70, and I'm going to do this all in one step. 758 minus 70 times 33.1 gives me a b of negative 1,559. All right, so what's my equation look like? There's b, there's m. So the equation that I have found, the linear model I have created, is y is equal to 70x minus 1,559. Now, let's talk about what this means, because this is a pretty big deal. Okay, so if you can correctly identify what this means for the problem, this is going to go a long way to explaining how this works. Okay. I was talking to a student in my office the other day, and the key part or the key point in algebra is that there are only, when we go to describe something that occurs in the real world, we can find functions and equations and graphs that match for some period of time, but we're never really going to find one that just gets it dead on. Okay, and take a look at this example first. I have 70x minus 1,559. That negative 1,559 would correspond to if I had 0 runs, which is x. If my on-base percentage was 0, then my runs scored would be negative 1,559. Is that possible? Absolutely not. Right? If I don't have any on-base percentage, if no one ever gets on base, I would score 0 runs, maybe some home runs, some single, some 1-run home runs, but that would actually count toward on-base percentage too. So no, it would just be 0. So this line is useful for us, but it's only useful in my data set over here in the values around x is 30 to 35. It doesn't do me any good when on base if I go for x greater than 100, because you can't have an on base percentage greater than 100, and it wouldn't do me any good for negative x because it doesn't make any sense. I can't have on base percentages negative, and it also doesn't make a lot of sense for me really until the runs scored comes back positive. Does that make sense? Does that concept, that idea make sense? This is a linear model, and if I want to use it, and again, I'm getting it from picking 2 points in my graph. If I want to use it to predict what's the on-base percentage what's the number of runs scored if on-base percentage is 35. So that means x is 35. So I'm looking at y is equal to 70 times 35 minus 1,559. Okay, 35, we don't have any values over here on the table that are all the way up to 35. I think we have 34.8. So we are expecting a number that's in or around the numbers in the table, but it's going to be better. 70 times 35 minus 1559 is 891. So this means if the on-base percentage is, if the on-base percentage is 35, estimated number of runs is 891. Okay. That's way up there, isn't it? Okay. Does it fit within our data? Does it make sense? There's a point, yeah, 34.8. We see one coming out to 820. I have another 800 here, 34.7. I have an 865. The problem is, though, when I created this linear model, the 2 points that are the closest to this example aren't included. The only 2 data values I took into account are the totals from Florida and the totals from Milwaukee. So all of this data is based on 2 data points. What I would love to do is find the line of best fit if I use all of the points. Okay, now that does not mean find the slope of every line, every pair of every lines. Okay, what it does, and I'm going to show you this in Desmos. I don't want you to think too much about this, but we're going to get a calculation of linear regression. Okay, and it's going to look like this. In Desmos, you have to type this exact phrase in. So y sub 1, you get downstairs by typing the underscore, that's shift, and the dash beside 0. Then there's a tilde right here. There's the slope m x sub 1 plus b. Okay, so here is what I'm getting from Desmos. And then let's convert that or show you what that looks like. Okay, so Desmos spits back these numbers. If y sub 1 is equivalent to, or what I'm looking for is the linear model. And I have 2 numbers here. I have my slope, my parameters, and my y-intercept. That's it, I just need those. They gave me the format. This is a linear equation, so I'm just going to plug these numbers, I'm going to plug them in up here. And I'm going to find my Desmos model says that the linear equation or the linear model should be y is equal to 49.2x plus negative 870, which is minus 870.94. Okay. Yes, we will go on to higher order problems in Desmos. So let's compare our model, where we had 891 runs, to this model. If x is 35, y is equal to massive difference, right? In both values. The slope is much more shallow, and the y-intercept is larger, right? Instead of being negative 1,559, it's just negative 870. Plug all that in, times 35 minus 870.94, and we find y is 851.06. So then for this model, if x is 35, y is approximately 851. I'm rounding it just because they're runs. They don't make a whole bunch of sense as decimal, but 850.06 is fine here too. And this is the OBP on base percentage, and then these are the runs. All right, which one of those is a better estimate, you think? Do you think the problem above is, or the problem on the one on the bottom is? Which one of these falls more in line with the data that we can see? Right. So let me show you where these are on the graph and then see if you can answer that question. If I list 35,851, you see it pop up over here? There it is, right there. That seems to fit along with our data. This is the point we get by following the slope or following the equation given to us by the Desmos linear regression. The other point was 35 891. Oh, that's in the wrong place. That's not even on the map. I'm gonna have to zoom out to get it. There it is. Okay. It's quite an outlier for us, right? It's way out there. So why is this one better? Why is this 851 better than the 891? Because it's more in line with what we have. That's the highest on base percentage that we see, but my runs are not so much larger than all the other values that they don't seem right. And the reason for that is this linear regression, what it does is it takes every point in here and it draws a line. And it's also called the line of least squares. And what that means is you get a line, and I'm going to show you. Here's the line. This is the other part. It graphs. What this does mathematically is it takes every point that is on the graph. It finds the distance between the point and the line, and then it creates a square where the top left touches the point, the bottom right touches the line, or if I'm down here, the top left touches the line, the bottom right touches the point. What it does is it goes through and finds what is the way to make the area of all of those squares the smallest number possible. So you're literally looking at this line is the equation. These are the set of points that are the least distance away from every point in the data set on average. So that's what this is doing. Okay, so this is as good as it gets. What about our line that we made up? For our linear model, we had 70x minus 1559. There's our model. Okay. You can see in that purple one, you can see how we're not getting that same benefit, right? This line is much farther away from this point or this point. It seems to be a lot closer. All the points above it are much closer to it, and the points below it seem to be far away. But look at what it does. It's hitting these 2 points because those are the 2 points we use to create the line. If I had picked a different point, I would have a different line. I could have a line passing through these two. So all this to say, the linear regression takes into account every single point and draws a line based on all of the data you have. The linear model we created only took into account 2 data points. So whenever I get a chance to use linear regression, I do. And because it's just better, because it considers every single point instead of just the 2 points that I need to draw a straight line. All right, so that's 1.5. Any other questions on that? Okay. All right, then let's go to 1.6 and let's start talking about transformations. So in 1.6, we're starting out with some basic functions. So first off, you have linear functions on the left. Linear functions have the slope. That's if it's positive, it's rising from left to right. If it's negative, it's falling from left to right. If it's 0, the slope is 0, it's a constant function, which you see on the graph here. And if it's a vertical, it's not a function. So that's a key point here. We're starting out with basic functions. Everything here has to be a function to start with. So I've got a linear function, a constant function, and then some of everybody's favorites. We have the identity function. F of x is equal to x. Why is it called the identity function? Because if you plug in x, you get back x. That's what you get back. All right. Quadratic. And each function comes with a set of points. Here's the x value. Here's the corresponding f of x value. Remember, f of x is fancy y. Y equals x. F of x equals x. They mean the same thing. Got a quadratic. Got a cubic. You got a square root function. You got a cube root function. Absolute value function and a reciprocal function. Okay. Absolute value has that sharp V in it because what happens when I hit 0, once I start, as x goes toward the negative, it's kicking back that positive number. As x goes off toward the positive, it's kicking back that positive number. All of the points are above the x-axis except for 0, 0. Why is that? Because absolute value can't return negative numbers, right? Having a y value that's negative doesn't make any sense for absolute value. The reciprocal, on the other hand, is 1 over x. When x is positive, looks like I'm up here to the right. When x is negative, I'm down here. All right. Square root function is one of the slowest growing functions. It is increasing, but it just does it very slowly. All right. The square root of 1 is 1, of 4 is 2, 9 is 3, 16 is 4. See how x is rising quickly and y is not rising as fast. So that's why you have slow growth. Whereas for the quadratic and the cubic, as x gets larger, y is getting larger even faster. Right? X squared, 2 squared is 4, 3 squared is 9, 4 squared is 16. You see how the y value is growing. So this one we see that quick uptake. Okay, so these are our base functions. Having the numbers in here will be helpful for us. So let's figure out what in the world does transformation mean. Okay, well, if you give me all of those base functions, I can create any function that you want to by manipulating the base function. So I can do, and here are the 4 of the things, and I got 2 more under it. I do a vertical translation by, I have y is equal to f of x is my base function. So if I add k to the outside, what am I doing? I'm saying, well, when x is 0, let's pretend like this is the linear equation. If x is 0, y is 0. Well, now I'm saying if x is 0, f of x is 0, but I want you to add k anyway. So no matter what happens, I'm going to move up k units. So this is going to shift that base function or mother function up k units. If I subtract some number off the end, it's going to shift it down those units. All right, so that's my vertical move. If I add something, and notice this is on the outside, right? Y is equal to f of x plus f of x plus k. That plus k is on the outside. That's why I'm impacting the y value. I'm moving up and down. On the inside, it goes backwards. So if I want to shift the graph left or right, I have to manipulate inside the parentheses. Okay, it looks a little weird, but it does hold. So if I add h on the inside, before when we added something, we moved up, and when we subtracted, we went down. That fits in line with what we're used to, but now it's going to go the other direction. If I add on the inside, I shift to the left. If I subtract on the inside, I shift to the right. Okay, this one's going to make a little bit more sense when we get into the example, so don't worry too much about that now. What I just remember, if I add to the outside, it's up. If I subtract to the outside, it's down. If I add to the inside, it's left. If I subtract to the inside, it's right. Okay, so that's all my up, down, left, right. And then I have reflections. So if I have a function y is equal to f of x, if I want to make the graph y is equal to negative f of x, what am I doing? I'm taking the function and I'm making all of its outputs negative. If this was an output of 1, now it's negative 1. If it was an output of 4, now it's negative 4. If it was an output of negative 3, now it's negative 3, which is 3. Okay? So if you stick a negative on the outside, I'm reflecting across the x-axis. That means I just take my graph and I just rotate it around the x-axis. So whatever was above goes below, whatever's below goes above. To do a horizontal reflection about the y-axis, that's just like a page turn for us. The negative goes on the inside, right? So we're seeing a pattern. If I want to manipulate the graph vertically, I'm going to mess with the outside of my base function. If I want to manipulate the graph horizontally, I manipulate the inside or the interior of the function. Really, for us, the interior of the function, this f of negative x, I'm manipulating the input, right? Because remember that notation, f of x, that's whatever goes in parentheses, that's my x value. whatever comes out to the y. I manipulate the input so that the output is changed. Okay, stretching and compressing, all that's comes from multiplying and dividing, mainly just multiplying. If I want to do a vertical stretch, I'm going to multiply on the outside. So that's what you see here, a times f of x. If I want to manipulate horizontally, I multiply on the inside. So now y is equal to f of ax. So a horizontal stretch or compression comes from multiplying on the inside. A horizontal stretch or compression, or vertical stretch or compression comes from multiplying on the outside. Put it all together, and this is what we have. So these are all the letters that we've manipulated or used above. This is y is equal to f of x, but I've changed, or I've given every single possible value in here a letter, and those letters match up from above. So if y is equal to, so first off, if I take f of x and I subtract h, that's going to move me to the right h units. Adding k on the outside moves me up. So this k, this addition of k, if it's positive, I move up. If it's negative, I move down. This h, right? If I'm on the inside and I want to go left or right, this is where that h comes into play. So if I want to move 3 units, I need x minus 3. Minus 3 looks like it's going to move left, but it's going to move right. If I want to move right, then the inside needs to be negative. The other manipulation, the stretching, compression, all come from if I multiply the outside by a, now I'm looking at a vertical stretch. Or if I multiply by something between 0 and 1, I'm looking at a compression. And then the b on the inside there is where I get that horizontal stretch and compression. All right. That is not going to make sense until we do examples. Okay, but I've shown you all of the possible transformations. So just like we have order of operations to make sure we all get the same answers when we do math, right? Parentheses, exponents, multiplication, division from left to right, addition and subtraction from left to right. We created that so all answers are the same. Will there be questions on transformations on the test? Probably. Yeah, the tests, I could definitely see some transformations on here. All right. So to keep our order of operations happy, we are going to use horizontal we're going to do them in these orders. I'm going to do my horizontal. Hang on. X equals 35. Will there be questions on the transformations? No, if it's in the homework, really the best way to study for the test is doing the homework and then look at the review. So if the question is valid and if the question does exist in the homework, yeah, it could be on the test. If you don't see it in the homework and you don't see it on the review, don't look for it on the test. The only reason I do like that is extra credit, but that just seems mean. So order of operation here for transformations. If I have a problem where I have multiple transformations occurring, the first thing I'm going to do is my horizontal translation, and then horizontal and vertical stretch and shrink, reflect, and then vertical translations. So when I say horizontal translations, that's moving left or right. Horizontal and vertical stretches and shrinks, those are the multiplications. Reflections across the x and the y axis, that is the sign of a and b. And then lastly, that vertical translation is the k. So let's label the values that are doing this. Horizontal translation, that is all about the h. Okay. So take a look at my graph here. This is step 1. All right. Horizontal and vertical stretch and shrink. So since I'm on the inside, let's do that one first. The next thing I'm going to deal with is B, right? If I've got some multiplication on the inside, and then I'm going to deal with A. Next is reflections across the y-axis. So this is the sine of A and the sine. If you spell sine wrong, you get sing. And the sine of B, right? The sine determines if I've got a negative on the inside, I'm reflecting across the y-axis. If I have a negative on the outside, I'm reflecting across the x-axis. And then the last one is that vertical translation or shift, that's k. So if I give you a function that has some manipulation done to it, and you tell me how do I get from the base, or how do I get from this back to the base, or from the base to that, this is the order I'm going in. I'm messing with h first, then a and b, then the sign of a and b, and then vertical translation k. So let's do a problem. Okay, here's a graph of some function f of x. I don't have the function written down. I just have a graph. Okay, so below I have basic function notation. The graph above, this black graph right here, is f of x. Make it smaller so we can get everything on the page here. Okay, so there's my graph. It's a parabola, it's facing up, and it has a vertex at 2, 1. Okay, we're asked to perform the indicated transformations. So f of x plus 1. Well, in this one, k is 1. I have to do something else here, right? Is everybody cool with that? All right, k is equal to 1. And that means what? Adding 1 on the outside is a vertical shift or translation up 1 unit. So what happens to my graph? Okay. Well, the base or the vertex was at 2, 1. Now the vertex is at 3, 1. Okay, and everything makes that move. So for my first one, let's get, all right, so there's number 1. There's the new vertex, and I'm going up. That's horrible, horrible drawing, but you get the idea. Okay, so my vertex shifts up 1 unit. That's all that happened. Everybody understand that idea? Again, I don't have a function for f of x. I just say f of x, and I'm using those rules for manipulation from the last page. The second one, on the outside, I have f of x minus 6. All right, so got the same thing. K is negative 6. So what do you think that's going to do? It's a vertical shift. Now I'm going to go down 6 units. Okay. Nothing else changes. No directions change. No nothing. But the whole parabola comes down 6 units. Okay. Let me show you what it looks like if I just do the base point. So the point for the first one that I started with, my original vertex is 2, 1. And then I said k is 1. So what does that do to me? That changes the y value by 1 unit. So now I'm looking at 0.22. In this one, I have f of x minus 6. I start out with the vertex of 2, 1. If k is negative 6, that means I am taking the y coordinate and I'm going down 6 units. I'm bringing those points down. So now my vertex is at 2, negative 5. How about the next one? Okay, f of x plus 5. This is the first time we've seen it on the inside. Okay, so what's living here, or what letter from our previous work corresponds to that addition on the inside? Well, that's h. So I got h is 5. I'm messing with the inside, so this is a horizontal shift. and it's 5 units, which direction? Messing with the inside, I'm either moving left or right. This looks like it moves to the right, but remember when things are on the inside, they're flipped. So this looks like I'm moving right 5 units, but I'm actually moving left. Okay. So what does that look like for us, or for our plot? So I have 2, 1. And here's the thing, and this is where it can get a little confusing. Take a look at this base. If I show you this original piece right here, look at the sign on the inside. This is x minus h. So in this problem, when I have x plus 5, this is supposed to be a minus when nothing has occurred. It's a plus, so that means h is negative 5, right? It looks like a move to the right on the inside, but it's actually moved to the left. H, the sign of h shows that. So what do? I take 2 and I subtract 5. So now I have the point -3, 1. So before, when I plugged in 2, I got out 1. Now when I plug in -3, I get out 1. Why? Because I started out at 2, I have to move 5 units to the left, and now I'm over there at -3. All right. So let me be super clear here. This is f of x minus -5, and that is h right there. Okay, so that's why that happens. It looks backwards on the inside because it's supposed to be subtraction on the inside. Okay. So let me pause it here because there's a beeping going on outside my door because this door has been broken today. You take 2 minutes and knock out the next 2. Tell me what the transformations are, and then we'll come right back. All right, still have no idea what that beeping is. All right, so let's take a look at top right here. I've got f of x minus 1, minus 4. I have 2 things going on at this time, right? I have h is what? It's supposed to be minus 1 in here, so that means h is 1. All right, and I have k is -4. What did those things do before? When h is 1, that is a horizontal shift right 1 unit. Again, if you're used to it being backwards, if you want to think of it as being backwards, take a look at take a look up here. This is -1. It looks like it's going to move left, but it actually moves right. And then the k is -4. When I'm messing with the outside, everything goes exactly like it looks like I'm subtracting 4 on the outside. So that's a vertical shift down 4 units. What does it do to my point? My point, again, my vertex starts out at 2, 1. H is 1, K is -4. So the H gets added to the X value, and the K gets added to the Y value. So now I have the point, what? Now I'm looking at 3, -3. Right? And this is my new vertex. What's happened is my parabola has moved. On all 4 of these examples so far, all I've done is move left, right, or up, down. All right? So now let's start making some changes. Now I have taken f of x, I've done 2 things. Okay? I've done one thing that I'm used to, and then one thing that I haven't seen before. So I've got 2 manipulations here. H is on the inside. It is -3, which means a horizontal shift to the left 3 units. Again, I'm adding on the inside, so it looks like I'd move right 3, but I actually move left 3. And then here's the new thing. I've put a negative on the outside. That negative corresponds to, and I'm going to jump back to that big formula, that negative is A. It's the number that I multiply the outside by. Okay, so that means A is -1. Okay, I have messed with the outside, so that means this is going to impact my graph vertically. All right, remember, messing with the outside has vertical impact, messing with the inside has horizontal impact. So I multiply the outside by a negative. My rules tell me that if I have a negative on the outside, that is a vertical reflection across the x-axis. So vertical reflection across the x-axis. What is that going to look like if I graphed it? Okay, so if I take my point and I do both of these things, I start out again at 2, 1. And the problem tells me to take things in order. So the first thing I'm going to do is the horizontal shift, because that's what the order of operations said to do. Let's make sure we get that right. Horizontal shift, horizontal vertical stretch, then reflections. So we're going to deal with this one in 2 steps. First thing I'm going to do is say H is -3, which means I'm now at the point, what, to -3, which is the point -1, 1. And now A is -1. So what did that do? Well, I multiplied on the outside by a negative. I said that manipulates the Y value. So now I'm at the point -1, comma, I take the Y value and multiply it by -1, and I now find myself at the point -1, -1. Okay? Questions? Seems good? All right. Yeah. So this is my new vertex, and my parabola points down, right? So what happened here? This caused a shift to the right by 3. How does the vertical reflection change the points? Excellent question. So let me show you. Let's come back to the base graph. And let's deal with the one I just did. So the one I just did was -f x plus 3. So x plus 3 takes my vertex. No, it takes my vertex and moves it 3 places to the left. 1, 2, 3. So here's my vertex now. And then A is -1, so this is reflect across x-axis. Okay, so that means this point was here. Now take everything that's up above the x-axis, move it to below. Everything below, move it to above. -1, 1 corresponds to -1, -1. So now the vertex has gone down here, but remember, until I do the multiplication, this is all I did is move left 3 units. So right now my parabola faces up, but then when I multiply by that -1 on the outside, when I plug in -1, I used to get out 1. Well, now when I plug in -1, I get out -1. When I plug in 0, I used to get this number here about positive 2.5. Well, now when I plug in 0, I get -2.5. So there's that point. Same thing on the right, and then you'll see there's the transformation. Okay, that's the multiplication by -1 that takes the parabola that was facing up and now faces it down and flips the vertex. It's one unit above the x-axis. I do a reflection across the x-axis. Now I'm 1 unit below the x-axis. So this is -f of x plus 3. Okay, how's that feel? All right. Still, it's the new shoes. Still getting used to bringing a pair of shoes. You still got to work them in a little bit. Good. Okay. So last one, f of -x plus 2. This takes care of all the variables or all the stuff. There's some rules. Yeah. Yes, we're gonna have a lot more manipulation in there. On the inside, we haven't seen this yet. I've flipped the sign on the inside. If I go back to my notation, that is the letter B. So for this problem, B is -1, and we're used to this, K is 2. Now, K is 2, that's vertical shift up 2 units. But that -1 on the inside, when I multiply by something on the inside, or when I multiply by a -1 on the inside, guess what I do? When I multiply by a -1 on the outside, that caused me to do a vertical reflection across the x-axis. Well, when I multiply the inside, it always impacts the horizontal. So I'm doing a horizontal reflection across the y-axis. Okay, so what does that do to my vertex now? My vertex for f of x started at 2, 1. I do the vertical shift is the last thing I do, so I actually apply b is -1 first. So b is -1, that manipulates the x coordinate, right? So now when I was at 2, now I'm at the point -2. And then k is 2, which means the vertex moves up 2 units, 1 plus 2. And now I have a vertex at -2, 3. Questions? Let's look at it on the graph, especially because these are the ones that have a lot of manipulation going on. Again, I'm starting here at I keep calling this 2-1 and it's 2-2. No wonder none of this stuff's matching up. This is 2. No, this is 2-1. Never mind. What am I talking about? I'm looking at the red one. This is 2-1. I do I don't flip over the x-axis. I flip over the y-axis. So what this does is it takes all these points. Let me just erase and we'll come back out. We can always just remanipulate, or you can look back at the video to see what we were doing before. The first thing is I'm at the point 2-1, and I say multiply the inside by -1. So now I was at 2, or I was at 2-1. So now I'm at multiply that by -1, and I land at -2-1. Right? That's the flip across the y-axis. All these points just hop over the other side of the y-axis. I was 2 units to the right of the y-axis. Now I'm 2 units to the left of the y-axis. And then I add 2. Right? So I went from 2-1 to -2-1. And now 1, 2 units is -2, 3. So now my vertex is here. I shifted or did my transition or my reflection across the y-axis. So the parabola was facing up before. It's still facing up now. Okay, it's still facing up, but it's now on the other side of the y-axis because that's that reflection across the y-axis. All right. So that's the manipulation, and this is helpful. I like doing it this way first, where I don't show you the functions. I just give you f of x and show you how a, b, h, and k can all manipulate the graph, and then we go and tackle some problems. So in the practice, use translations to graph the function defined by q of x is equal to x, the square root of x plus 2 minus 5. Now, what is the parent or mother function of this? Okay, so this is another step. The base function here is the square root of x. All of the parent functions or the base function or the root functions, you'll hear me say, all of these words, base or root, they all mean the same thing. Base function, root function, parent function, mother function, any of those are fine. This starts out as y is equal to the square root of x. And then I just do what this page tells me to do. If I add to the outside, I do this. If I subtract to the outside, I do this. If I add to the inside, I do this. If I subtract, I do this. If I multiply on the inside, I do this. If I multiply on the outside, I do this. So on and so on and so on forever. So come back to our base. Here's our base. And remember, we just had 8 functions here. There are more, right? If you had a 4th degree polynomial, you would, or 4th degree root, you would have more of these. But there's our root. There's our square root function. So this is what we look like to start with. We look like this. We're rising, starting at 0, 0, rising up from left to right. So if I go back to my graph, my parent function is the square root of x. What are the 2 manipulations here? Obviously, on the outside's always nice because k is -5. And then on the inside, h is -2. Remember, it looks weird. On the inside, it's supposed to be h minus, or x minus h. It's plus, so that means this is x minus -2. So h is -2. So that's what I do first. Let me actually put that first, because we do the interior first. H is -2. That means that's a horizontal shift. Look back at the original problem. This looks like it's going to the right. So it goes to the left 2 units. And then k is -5. That is a vertical shift down 5 units. All right, so I start here at the origin because that's where my parent function starts. I move 2 units to the left and 5 units down. Here is the beginning or that starting point of my graph. What's going to happen? I need more points on here to make so that I can draw it. Well, it's just going to have that same exact shape. It's just going to start down here because I didn't multiply on the outside by anything. I didn't multiply on the inside by anything. So all I did is take that parent function, shift it left and down. So it's still going to look like this, right? I started, and if I can try to hit some on the way, 1 is 1, 4 is 2, 9 is 3. There's the square root function, so it's moving like this. I've shifted it down and to the left, but it's still going to take off at that same rate. So it's going to look like that. Does that make sense? This is the new, and this is the parent. Okay. You can find points on the new one by plugging in values for x. So if you want to put q of 0, what happens? When I plug in 0, I get the square root of 0 plus 2 minus 5. That's the square root of 2 minus 5. Square root of 2 is 1.4 something. 1.4 minus 5 is negative 3 and some change. That's where we landed, negative 3 and some change. All right. So this is how it affects my function. All right. Next, and this will be the last one because I know everybody's on the edge here. First off, I'm going to graph f of x is x squared. When 0 is 0, there's that beeping again. 1 is 1. Negative 1 is 1. Positive 2 is 4. Negative 2 is 4. And then there's my parabola. Right? So it goes up like this, and it goes up like this. On these, on the homework, yes, on the test, we'll see. Okay, to check your graphs. I would rather see it on the check, but yeah. What is this doing? Okay. So this is my root function. I'm multiplying, but I'm multiplying on the outside. I'm impacting y. So this means a is 3. Okay. So when a is 3, that means I take my y value and I multiply it by 3. Whatever I got out originally, I get out 3 times that. 0, 0 stays 0, 0. But when I plug in 1, what do I get now? I get 3 times 1 squared. Up above, 1 squared is 1, so I have the 0.11. Well, now 1 squared is 1. Multiply that by 3. Now I'm looking at when I plug in 1, I get out 3. When I plug in negative 1, I get out 3. See how this is going to rise faster? Right? It's a steeper parabola, right? So when I multiply by the outside, that impacts my y values. And that makes it, that's what we call that vertical stretch. So I'm taking that graph and I'm stretching it vertically. All right, so we'll call it there. We have another page of practice in 1.6 we'll talk about, and then we'll see how we're going to tackle 1.7 and 1.8. But for now, don't worry about the test at this point. Let's just get the material out of the way, and then we'll see how. I'm going to give you every opportunity and all the chances in the world. I'm not going to ask you to do something I don't. That's ridiculous of you. So don't let the testing worry you. Focus more on dealing with these transformations because they are important concepts, but it's going to take practice. It's just like everything else in this class. It's going to take practice. It's going to take time. All right. You all have a great weekend and enjoy the time off, and I'll see you again a week from today.